Mr. Smith here with reading quizzes 17 and 18 on polar equations and what they have to do with calculus. I've decided to combine the two reading quizzes into one video because we're going to do a lot of talk in class about what calculus has to do with polars. So I'm giving you the overview here, a pretty quick video. So how do you find a polar derivative? Well, it's important to realize that there are many different types of derivatives that could relate to polars. For example, dy dx would tell you the slope to a polar curve, whereas dr d theta would tell you how the radius length changes as the angle changes. And those are two very different concepts which we'll look at. dy d theta and dx d theta tell us how the x and y coordinates change as the angle changes. The one we're going to do a lot with is the first one, dy dx, because if we need to find a tangent line to a polar curve or just find the slope of the polar curve at a certain point, then dy dx, as always, is what we look for. Dr d theta will be very helpful if we have, for example, a particle moving along the path of a polar curve, and dr d theta would essentially tell us how quickly the radius changes as our angle changes. So how do you find dy dx? In order to find dy dx, we relate our polar derivatives to what we did with parametrics. That is, dy dx is equal to dy d theta over dx d theta, with the parameter, in quotes, being theta. So then the question is, how do we find dy d theta and dx d theta? So that goes back to our conversion formulas, which we talked about in our lab. Y is equal to r sine theta, and x is equal to r cosine theta. So that means that dy dx is as simple as finding the derivatives of these two formulas. The derivative of r sine theta, which we could find by product rule, r cosine theta times, or excuse me, r cosine theta plus dr d theta times sine theta. And the reason why we have a dr d theta is because we're taking the derivative with respect to theta as opposed to r. Similarly, dx d theta is equal to negative r sine theta plus dr d theta cosine theta. Typically, you'll have some sort of an r that you'll know. Like in class, for example, we said that r was equal to cosine theta. And so you're going to be using the product rule a lot to find out what dx d theta and dy d theta are. So therefore, dy dx is dy d theta over dx d theta. Your book has the formula in it for a polar derivative, which is something that you can just memorize, or you can remember that the formula comes from our conversions, and so all you need to do is essentially derive it each time, but you only need to know what the conversions are. So here's an example. Consider the cardioid r is equal to 1 plus sine theta. First part, find the slope of the tangent line when theta is equal to pi over 3. So the first thing to notice is this is a polar equation, and so we need to remember our conversions. X is equal to r cosine theta. When you plug in r is equal to 1 plus sine theta, you get x is 1 plus sine theta times cosine theta. And y similarly is 1 plus sine theta times sine theta. So our conversions are very useful to getting everything in terms of theta. When we do that, then finding dy d theta and dx d theta is just a matter of the product rule. In the case of dy d theta, the derivative would be 1 plus sine theta times the derivative of sine theta plus the derivative of 1 plus sine theta times the sine theta. And we end up with the formula that's in the numerator in the dy dx shown. Similarly, we can find dx d theta by using the product rule. When we plug in theta is equal to pi over 3, we use our wonderful trig knowledge and find out that the derivative is negative 1 at this point. Alright, part B, find the points on the cardioids where the tangent line is horizontal or vertical. So just like with parametrics, to find points that are horizontal, we're going to set dy d theta equal to 0. And if you remember from the previous slide, dy d theta is the numerator here, which I've cleaned up to say as cosine theta times 1 plus 2 sine theta. We're going to set that equal to 0 and use our trig knowledge to find our points. The cosine produces the zeros of pi over 2 and 3 pi over 2. The 1 plus 2 sine theta produces zeros of 7 pi over 6 and 11 pi over 6. To find vertical points, we're going to set dx d theta equal to 0. Alright, and if we simplify the denominator here, we're going to end up with cosine squared theta minus sine squared theta minus sine theta is equal to 0. A quick little trig substitution of one of our identities will show that cosine squared theta is equal to 1 minus 2 sine squared theta, which we can then factor into 1 plus sine theta times 1 minus 2 sine theta. And our solutions from that are 3 pi over 2, pi over 6, and 5 pi over 6. So one thing to note is that at 3 pi over 2, both dx d theta and dy d theta are equal to 0. So at that point, the type of tangency, whether horizontal, vertical, or otherwise, is inconclusive at that point. But we can conclude that we have horizontal tangents at pi over 2, 7 pi over 6, and 11 pi over 6, because the dy d theta is equal to 0, but dx d theta is not. And at pi over 6 and 5 pi over 6, we have vertical tangents because dx d theta is equal to 0 there, but dy d theta is not. So one final thing, dr d theta, what does that have to do with anything? So consider that equation, r is equal to 1 plus sine of theta. Finding dr d theta, which is cosine of theta, is not very difficult. Notice this is very different from finding dy dx, where we had that very complicated formula, okay, where we had dy dx is all of this quotient here. The derivative, dr d theta, tells us how the radius changes as theta changes. And I put a nice little chart in here that helps describe that. If r is bigger than 0 and dr d theta is bigger than 0, that means that the radius increases, so we're moving away from the origin in that case. If r is positive and dr d theta is negative, on the other hand, that means our radius is getting smaller and our particle moves towards the origin. Opposite happens if r is already negative and dr d theta is positive. That means that r is increasing, which means r is getting negative, is still negative, but is getting closer to 0. So our particle moves towards the origin. And then opposite if dr d theta is less than 0. Okay? So your reading has various other situations that you might find helpful. Okay. How do we find areas with polars? And this is where it gets a little bizarre, and we'll do a demonstration in class which helps to show this. But you just have to realize that the polar way of thinking is circular, not rectangular. So in the diagram that I've got here, we've got a circle, which will be our polar graph here. And I've cut out what's called a sector of the circle. And the sector of the circle is in yellow. And it's really a portion of the circle, in this case with an angle measure of theta. We'll talk in just a second about why I have d theta here. But the angle we'll call theta in this case. All right? This sector is a portion of a circle. All right? And some things to remember. Obviously, the area of a circle is pi r squared. But the slice, the sector given in the diagram, has theta over 2 pi portion of the circle. Why theta over 2 pi? Well, because the portion of the circle that we're doing is the theta portion, and the entire circle has radians of 2 pi. So this is kind of the fraction of the circle that we're dealing with. The area of this sector, therefore, is theta over 2 pi times pi r squared, which can reduce down to 1/2 theta r squared. And so our idea of finding areas in polars is we're going to find the areas by adding up all of these different sector areas. And when we do so, we get our complete formula, which is theta 1, the integral from theta 1 to theta 2 of 1/2 r squared d theta. And the d theta comes about when we actually, just like with the rectangles, deal with a minute width of angle. So here's an example. Find the area of the region that lies inside 3 sine of theta, which, as you remember from class, will be the circle that with diameter 3 that lies on the y-axis. And outside, r is equal to 1 plus sine theta, which is the blue graph, which represents our favorite curve, the cardioid. So inside, r is equal to 3 sine theta, and outside, r is equal to 1 plus sine theta will be the area outside the blue, but inside the red curve. All right, in order to find the area between two curves, we're going to find the area of f of theta, which is the outer function. That'll be the red circle, or the r is equal to 3 sine theta, minus the area that we get when we do 1 plus sine theta, which is the blue function. We'll call that g of theta. Find the area of the region. So it takes a little bit of work first to figure out what the limits are. In this case, the intersection points are what define the limits of the integral. So that'll be where 3 sine theta is equal to 1 plus 2 sine theta, making theta equal to pi over 6 and 5 pi over 6. So those two angles at pi over 6 and 5 pi over 6 will be where our boundaries are of our region. So it's important to realize, as I'll demonstrate in class, that in order to find the area, we are rotating a ray around the plane. Okay, so wherever that ray hits the graph, that's kind of the sector area that we're accumulating. So when It's a little bit different than accumulating rectangles, and we'll have a little bit of problem at first trying to understand exactly what region we need to find. So we plug it into the area formula and evaluate. So we do area is equal to 1/2 times the integral of pi over 6 to 5 pi over 6 of 3 sine theta squared d theta, and plug in 1 plus cosine theta as well. And just like with any other areas, we're going to subtract the outer area minus the inner area. It just looks a little bit different because we're squaring, and that's just because of the polar formula. So the area ends up being pi.